Hey, what's up guys? Welcome back to the channel. So today's video is about the problem longest palindromic subsequence. Again a standard DSA problem guys, and again based on the same concept, which is dynamic programming and longest common subsequence. So let me start with the problem statement. Now it's pretty simple and straightforward. It says that given a string and you have to find the longest palindromic subsequence, right? So what exactly is a longest palindromic subsequence? Well, we know what is a palindrome. A palindrome is basically a string that reads same as forward and backward. So if I write a string race car, then doesn't matter whether you read from left to right or right to left, the string is going to remain same, right? So we have to look for palindromic subsequences. Now again, what is a subsequence? So if you have seen my previous video, then I have already explained a subsequence, but let me explain it again. So I have this example, right? A subsequence is basically a sequence of character that I have randomly picked in a order from left to right. So let's say I pick this one, after this I pick this one, then I pick this one. So BCA is one of the possible subsequence, right? After this, let's say I pick this one, then I pick this A, then I pick this A and then B, right? So this is going to give me B, A, A, B, right? After this, I can pick one more sequence. So let's say I have A, then I pick C. So AC is again one of the possible subsequence. Then I can pick something like BCB, right? So BCB is again possible subsequence. So there are multiple subsequences possible like this, right? And now our task is to look for the longest palindromic subsequence, right? So if you notice here, then out of these subsequences, there are some subsequences which are palindrome, right? You can see here that whether you read from left to right or right to left, the like subsequence is going to remain same. So this is what a palindromic subsequence is, just like a palindromic string, right? So we have to look for the longest palindromic subsequence among all possible palindromic subsequences. So let me try to write one. Let's say I pick this B. After this, I pick this A, right? So after this, what I can do is I can pick this B again, then I can pick B, then I can pick like A and then B, right? So this is a palindromic subsequence which is of length like 1, 2, 3, then 4, 5, 6, like 6 is the length here. So can we make it longer? What I can do is I can choose B, A, B, then C in between, right? So I can choose C in between, then again B, A, B. So this is going to give me a like subsequence of length 7, right? And it's a palindrome. You can see here that like left to right or right to left, both reads the same. So 7 is going to be the output for this particular example. Now I hope you have understood the problem well. So let's talk about the solution now. Okay, so here I have written the same example as given in the problem statement, right? And according to the problem, we have to look for the longest palindromic subsequence. And we know a palindrome is a string that reads same as forward and backward, right? Or let me tell you one more thing, that if I have a palindrome, let's say I have palindrome AB, BA, right? Then one thing about palindrome is the reverse of palindrome is equal to the palindrome itself, right? So if I write the reverse, then I'll have AB, BA, right? So you can see that both of these are equal. So reverse of a palindrome is always equal to the palindrome string itself. So now what I can do is, from this string, I can choose any subsequence. Let's say I have this B, B, and then A, right? So I have B, B, A. My question is, what's the guarantee that the reverse of this particular subsequence is equal to the subsequence itself? Because only in that case I can say that it's a palindromic subsequence, right? So first task is to look for a palindromic subsequence. So I need some way to get to know that this is a palindromic subsequence, right? So what I can do is, one way is to write the same, first find this subsequence, then write it in reverse, right? So I'll get ABB. And now I can say that it's not a palindromic subsequence. But hold on. First we are looking for a subsequence, then we are writing in reverse. Instead of doing this, I can look for the same string and I can start traversing from the back simultaneously, right? So when what I can do is I can start traversing the string from the front, and then simultaneously I can start traversing string from the back, right? And then when I choose some indices for being like a subsequence, then I'll automatically get the reverse. Let's see how. Let's say I have BBA, right? I have these three values. So when I choose these three values from the back, then I will have first A, then this B, then B, right? So this is how I can automatically get the reverse of the given subsequence. I don't have to reverse it explicitly. Once I have done this, I can simply check whether these two subsequences are equal or not, right? Make sense to you? Okay, so now instead of like traversing the same string, I can write this particular string in a separate like variable in a reverse order, right? So let me write this. First of all, let me remove all the extra stuff that I have here, right? So this is the kind of intuition that we need to build in order to like get to the approach, right? So what I'm going to do is I'm going to write the same string in reverse order. So I'll have B, A, C, B, C, B, then A, B, B, right? This is the same string in reverse, so let me call it reverse string. Okay, now I'll start traversing the same string simultaneously, right? So I have I and then J, and then I'll simply look for the subsequences which are equal. Why I'm saying the subsequences which are equal? Because see, whenever I choose a subsequences from this particular string and this string, then one thing is sure, that this subsequence and this subsequence both are reverse of each other, right? And in case they are equal, so I can say that they are a palindromic subsequence. Let me show you one example. So let's say I choose this A, okay, I choose this B, then A, then B, right? So same here, I'll choose, okay, so I'll start with this, like, okay, what I'll do is I'll first choose this B because I am starting from this point. After this, I'll choose this A and then this B, right? So this way, I'm getting BAB here and BAB here. So you can see that both of these are reverse of each other, right? So this way, okay, reverse of each other and equal as well. So I can say that, okay, I have got one palindromic subsequence of length 3, right? So this is what I need to do. I can write the same like same string in reverse, and then I can look for longest equal subsequence in this particular string, right? But there is one more thing to observe. When I say longest equal subsequence, then I'm talking about nothing but longest common subsequence only, right? So this is nothing but longest common subsequence. So now what I can do is I can simply write the code for longest common subsequence, and then I can simply pass the reverse of a string instead of passing a string 2, right? So in longest common subsequence, what we do is we generally look for the common subsequence in two string. I have str2 and then str1, right? But here I will have one string, and the second string will be the reverse of same string. I hope that makes sense to you, right? Now the question is, what is the approach that we need to follow in order to find the longest longest common subsequence, right? So if you're someone who have already solved this problem, longest common subsequence, then you are good to go. You can write the code, you can submit it, right? But if you're someone who don't have any idea about longest common subsequence, then in this video I'm going to explain that particular thing as well, right? So let me start. One thing that I want you guys to know is how we write all the possible subsequences of a given string, right? Because that the similar idea we are going to use in order to solve the problem. So let's say I have a string amn, right? So what we do is we generally start from ith character because we have to pick some character, and we have a choice. We can either pick this character in a like in a subsequence or not. So if I pick this character, then I will have a in the subsequence, and if I don't pick, then I will have an empty subsequence, right? After this, I'll come to the next point, right? And for the next point, again I have a choice. I can either choose or don't choose. So if I choose, then I will have am as the current subsequence, right? And if I don't choose, then I will have a as the current subsequence. And for this, if I choose this m, then I will have like m appended to the current subsequence, so I will have m, right? And if I don't choose the current character, then I will have an empty subsequence. After this, I'll come to the last point, right? And for this point, I have again two choices. I can either choose this n and append to the end of this particular subsequence, or don't choose this, right? So if I choose, then I will have amn, and if I don't choose, then I will have am only, right? And about this a, so if I choose, then I will have an, right? And if I don't choose, then I will have a single a. For this m, if I choose, then I will have mn, and if I don't choose, then I will have single m, right? And for this, if I choose, then I will have n, and if I don't choose, then I will have an empty subsequence. So these are the possible subsequence for this particular string, right? So now I hope you guys have got the idea how we print the subsequence of a given string. The game is of just include or don't include. So for every character, we have two choices, right? Now the similar idea we are going to use in order to solve the problem. Let me tell you how. So first of all, I'm going to remove this particular stuff, right? And after this, I'm going to write the same string as given in the problem statement. So for that particular example, let me write the string first. So I have a string as I have BBA, then BCB, then I have CAB, something like this, right? Let me see it. So I have BBA, then BCB, and CAB. Okay, now let me write the reverse of this string as well. So reverse is nothing but I have BAC, then BCB, then ABB, right? Now the similar idea we are going to use. We are going to start traversing from the first point, right? And let's call it pointer I, and let's call it pointer j. So pointer I is basically going to point to every possible character of string, and j is going to point to the characters of a reverse, right? Okay, now for every character we have a choice. We can either choose it or don't choose this. So if we have a equal character, right? So we are looking for the longest equal subsequence or longest common subsequence. So whenever we have a equal character, then we are definitely going to choose it, right? Now let me tell you what happens when we choose it. So let's say I have if my str of I equals to str of j. Okay, reverse of j, right? Reverse of j. So what happens when we have equal characters? So whenever we have equal character, we are going to include it in our answer, right? So let's say we have an answer subsequence, then I'll write b in the answer, then I will have this place empty, right? So after this, we are going to move to this place. Both pointers are going to move, right? And then we have to find the longest common subsequence for this particular answer. And let's say we have found the longest common subsequence for these particular strings, then we can simply append that particular string to the answer, right? And we will get the longest common subsequence because b is going to be surely in the answer, right? But hold on, we are not interested in the string, and all we are interested in is just the length of that particular string, right? So we are not going to find the string. Whenever we have equal character, then we will say that, okay, find the length of longest common subsequence for this, and whatever is the length, add 1 to that particular answer. Why I'm adding 1? Because I have found one character of that particular answer, right? So I'll write 1 plus, and let's say our function, there is a function which is going to give us the answer, right? So function is solve for I and j, right? Because I and j are our variables. So I'll write solve for now I plus 1 and j plus 1. I hope that makes sense to you, because initially I was at this place, and then I is going to increase, and then j is also going to increment, right? So this is what I will do. Then I'll say this is my answer, right? This is my answer. So this is what I can do whatever I have equal characters. But there is one more possibility. Let's say the characters are not equal, right? So let me remove this again. Let's say we don't have equal characters, so let me write the strings here. I have BBA, then BCB, then CAB, and here I have like BAC, which is the reverse of the same string, right? BCB and then ABB. Okay, and currently I'm pointing to these places. This is I and this is J, and I don't have equal character. Do I have equal characters here? But let's say these are not equal, right? So if these are not equal, then there are two possibilities. Either this character is equal to this character, or this character is equal to this character, right? I'm saying possibility. I'm not saying that any one of them must be true. I'm not saying that. I'm saying that there is a possibility that these any of like these two may be equal, or these two may be equal, or any of one of them is not equal, right? Something like this. So what I'll do is I'll say that I can either check for I and j plus 1, either this is going to give me the longest answer, or j and I plus 1, either this is going to give me the answer, right? So let's say this is solve for I plus 1 and j, right? And I have b equals to solve for I and j plus 1. You can notice one thing here, that I'm not adding 1 in this case. Why I'm not adding 1? Because see, we don't have equal characters, right? So in this case, our answer is not going to increment because we are not going to include that particular character which is not equal. Now I will have the longest common subsequence for like this string and this string, like this is for I and j plus 1, and I will have longest common subsequence for this string and this string. This is for I plus 1 and j, right? So out of these two, I have to return one answer. But which one? This is the question. See, I'm only interested in longest common subsequence, so that's why I will return the maximum of these two. So I'll simply say that, hey, return maximum of A and B. I hope that makes sense to you. So this is all we need to do in order to find the answer, right? This is a kind of recursive relation that we need to follow. Once you have found this, then I can show you the recursive code, right? I'm saying that this is recursive code because this is calling the same function again. So let's say I have a function which is going to take these 4 parameters. So this is what I need to do, right? And whenever we have a recursive function, then we must have a condition which is going to be a base case, right? And this is a base case, and even this makes sense. Let's say I have a string of length n. So whenever my j is equal to n, it is going to be out of bound, right? And for reverse as well, whenever my j is equal to length, then it is again out of bound. So in that case, I have to return 0. This is like, let's say I have a string ABC and I have an empty string, right? So what to do in that case? In that case, the answer is going to be 0, right? So this is what, this is how we can write the recursive approach to solve the problem, right? Now, I hope you have understood this particular approach. And what is the complexity of this approach? The complexity of this approach is very similar to O of 2 raised to the power n, right? Why? Because for every like problem or for every sub problem, we have two choices. Either we can do this or we can do this. And whenever this condition is true, then we have only a single choice, but we always consider the worst case, right? So the worst case is we have two choice every time. So whenever we have two choice n times, then it is something O of 2 raised to the power n, right? So this is the complexity which is not going to work for very large inputs. So we have to optimize it, right? Now before optimizing, what I want is I want to show you the recursive tree diagram for the given example, right? And with this, we are going to build some intuition for the optimal approach. Now let me start. For this example, let me draw the recursive tree diagram. So let's say I have initially I at 0 and j is also at 0, right? So I have initial function called as I and j, which is for 0 and 0, right? After this, I can see that the characters are not equal. So whenever the characters are not equal, so I plus 1 and j, or I and j plus 1, right? So I'm going to denote, I'm going to avoid writing this solve. I'm just going to write the values in the bracket. So I plus 1 and j is nothing but 1 and 0, and I and j plus 1 is 0 and 1, right? After this, for I plus 1 and j, which is 1 and 0, right? I is here and j is here. So for this, I can say that the characters are again not equal, right? This is b, this is d. So again, the same call, which is I plus 1 and j, this is going to give me 2 and 0, right? And I and j plus 1 will give me 1 and 1, right? After this, for this one, which is I equals to 0 and j equals to 1, I is 0 and j is 1, right? These two are again not equal. So again, I'll do the same call, which is I plus 1 and j and I and j plus 1. I plus 1 and j basically means 1 and 1, right? And I and j plus 1 basically means 2, 0 and 2, right? Well, that's enough. From this, I want you to make two important observations. The first observation is, see, the solution to every problem depends on the solution to sub-problem, right? So let's say I have found the solution to this and solution to this. So at last, I need to return the max of these two, right? This is what we have figured out from the recursive approach. You can see here, we are returning the max, right? Okay, so I can say that the solution to every problem depends on solution to sub-problems. So I can say that it's following optimal substructure, right? Substructure. The second thing is, you can see one more thing here, that we have some repeated sub-problems, right? We are calling function for 1 and 1, and then we are calling the function again for 1 and 1. This is like we are solving the same problem again and again. So this is something known as overlapping sub-problems, right? So these two are very important observation, and whenever we have these two conditions as true, so we can say that the problem is a dynamic programming problem, right? And one very important thing, guys, that not every recursive problem is a dynamic programming problem. We have to figure out these two conditions. These are mandatory conditions for a problem being a dynamic programming problem, right? Once we have found the dynamic programming problem, then we can apply two important approaches, either memoization or tabulation, right? So let me start with memoization. For the memoization approach, what we will do is, you can see here that we are solving the same problem again. So we are going to store the solution to this subproblem somewhere. Let's say I have stored it here in an array ARR, right? So after this, I will, before solving this problem again, I will check whether I have solved it or not, right? If I have solved it, then don't need to solve it again. Just get the answer from this array, right? I hope that makes sense to you. So I have written the code here. Let me show you the code. I have the memo like code here. This is the recursive code, right? And we are going to convert this code into memoization code. Let's see how. We know our answer depends on like ing every time, right? So we can store every possible answer in let's say array of ing, right? Because I and j are going to be unique for every possible problem. So this is going to give me like every possible solution stored in an array. Now one more thing is, what is the size of this array? So this is very important to figure out. Many students ask this question from me. See, what is the maximum value of I that I can have, right? So the maximum value of I can be the length of string, which is n, right? So we have to make the size of like rows as n plus 1. Why n plus 1? Because if I make the size n plus 1, only in that case I will have like n, right? I will be able to access the index n. And similarly for j as well, the size can be like n, so I can write n plus 1, right? So this is the size of array. Let me call it dp array because it makes more sense here, because dynamic programming problem, right? Okay, so once I have made this array, then I can store any sub problem in this array. How I'll store? So I'll simply write one thing like before solving this problem, I'll store dp of I and j, right? This means that for current I and j, store the problem in this particular index, right? So I'll store the solution. Similarly, I'll do for this as well, dp of I and j, right? And I can do it for this as well, but it's a choice, so let me do it for this as well. dp of ij equals to 0, right? And this is something that I will return. Okay, now once I have written these lines, so this means that I have stored my values somewhere in the dp array, right? Now still we have not applied the memoization technique. How we apply the memoization technique? Before solving any problem, we check whether we have solved it before or not. So how we will check? We will write if solved before. If this is the case, then we simply have to return dp of I and j. I hope that makes sense too, right? Pretty simple and pretty easy to understand, guys. Return dp of ij. Now the question is how to check whether the value is solved before, right? So one way is we can store null value everywhere in the dp, and if the value is not null in the dp, then I can say that the like the problem is solved for this, right? And then we can return that particular value. But instead of storing null, we can do one more thing. We can store -1. Why -1? Because we know that we are looking for longest common subsequence, right? So the answer will be at least 0 or more than 0. I can have any positive value, right? But I can't have negative value in my answer. So whenever the value is negative, then I can definitely say that the problem is not solved yet, yeah, right? So that's why we store -1 while writing the memoization approach. But this is not going to work whenever we have possibility for negative answer in the DP array. Always make sure that you have only positive values in the answer while making -1 in the array, right? Okay, now this is about the memoization approach. Let me show you the code now. Okay, so this is the code. You can see that I have written the code in C++, then in Python and Java, right? So the code is very similar to the approach. This is the memoization step. You can see that we are checking whether we have solved the problem or not, right? And this is where we are making the DP array. So this is about the memoization. Let me tell you about the complexity of the code, right? So the complexity of this approach is going to be O of n cross n, which is O of n square, right? Why I'm saying O of n square? Because we are not going to solve more than these problems, like this number of problem, dp of n and n, right? Because this is what the size of dp is, and we are not going beyond the size of dp in this particular problem. I hope that makes sense to you. So that's why the time complexity is O of n square. The space complexity is again O of n square because of this dp array, and n square because of this recursive stack as well, right? And this is something that we need to optimize, and this is what gives us an idea behind tabulation approach, right? See, we are having some extra space here due to the like recursive stack that we are following, because still our code is a recursive kind of code, right? So it is going to like utilize the system stack, so we have to avoid using that. And with this, let me talk about the tabulation approach now, right? Now let me write one example first. So let's say I have ABAC, and the reverse is going to be CABA, right? Okay, so now before I start explaining the tabulation approach, let me write the recursive code here. So the recursive code was, first of all, if I is equal to n and j is equal to n, right? In that case, we were returning 0. So I'll simply return 0 for this. After this, if my string of I is equal to reverse of j, so I'll simply return 1 plus solve for I plus 1 and j plus 1, right? And after this, if this condition is not true, like characters are not equal, so I have to return the max of two values. So I'll simply return max of like solve for I plus 1 and j, right? And then I have to return solve for j, okay, I and j plus 1, right? This is the recursive code, and our main main idea behind tabulation approach is to make this code something independent of the recursive call, right? Once it's clear to you, so let me start explaining the tabulation approach. First of all, let me write one more name for tabulation approach, which is bottom-up dynamic programming, right? Bottom-up dynamic programming. Now what I'll do is I'll write the reverse string in the column-wise manner. So I'll write C, A, then B, then A, right? Let me make columns as well. So I have columns like this. After this, I'll write the string in the row-wise manner. So I will have A, B, then A, then C, right? And this is the last index. This is the actually this is something which is equal to n, right? So this is not a valid index in the string, and even in the reverse as well. Okay, so now let me make the rows as well. Okay, so let me start with the last position first. Now, many of you guys face a common problem, which is from where to start traversing this DP array, right? Many of you guys even ask the question from me that why you are starting from last position, why not you are starting from the first position. So there's a reason. There's a reason. When we say bottom up dynamic programming, then what it means is, it basically means that we have to start from the base case and then we move towards solving the greater sub problem, right? So after this, at last I will have my problem solved at this particular index. Once you have understood this, so you will have complete idea about from where to start. Like if you have a different base case, then we can start from this position as well, which is the top right, or I can start from top left, or I can start from bottom right, or bottom left, or bottom right? So it totally depends upon what are the base cases. Okay, so now see, my base cases are I equals to n and j equals to n. So I'll start with I equals to n and j equals to n, right? After this, I'll first fill this row and then I'll fill this column. So let me fill it. For I equals to n or j equals to n, I have the value as 0, right? So I'll write 0 here. Okay, now I will come to this index while traversing the matrix, right? So when I come to this index, then I will check one thing. If my str of I is equal to reverse of j, so see, my str of I is c and reverse of j is equal to a, right? C is not equal to a. So in this case, I have to choose the max of I plus 1 and j, and I and j plus 1, right? What is I plus 1 and j? I plus 1 and j is basically pointing to like this particular index, right? Why I'm sure? Because I plus 1 is basically point to like the last index, and last index the problem is solved here. Similarly, like I and j plus 1 is going to point to this particular value, so I have to return the max of these two values, which is nothing but 0 again, right? Okay, now I'll come to this point. So again, b is not equal to c, so the value is 0 here. What about c and a? C is not equal to a, so the value is 0 here. What about c and c? The value is equal, right? So I have to write 1 here. Okay, now I will come to this point, and here a is equal to a, but the values are 0, right? So whenever the character is equal, so what we do is we do 1 plus and solve for I plus 1 and j plus 1. I plus 1 and j plus 1, basically this one, right? So this value is 0, so I'll write 1 here. So now let me convert this particular line to something independent of recursive call. So whenever my characters are equal, I'll write 1 plus dp of I plus 1 and j plus 1, right? Similarly, if these are not equal, then I have to write dp of I plus 1 j and I j plus 1. So this is dp of I plus 1 and j and dp of I and j plus 1, right? I have to return the max of this if the character are not equal. So let me completely fill this array. Now you can see that b is not equal to a, so I'll write simply max of these two. So max of these two is 1 here, right? After this, again a is equal to a. So whenever a is equal, like characters are equal, so I have to return 1 plus max of like this particular index. This is 0, right? Okay, now c is not equal to a, so I have to return max of these two. Max is going to be 1. Now I will come to these two values. So here you can see that b and a are not equal, so I'll return max of these two. So max of these two is going to be 1. After this, I'll come here, then b is equal to b, right? So I'll write 1 plus this value, right, which is dp of I plus 1 j plus 1. So I'll write 2 here. After this, what I'll do is I'll come to this index, then these are not equal, then max of these two values is 2 here. After this, I'll come to this index and not equal, then max of these two is 2 again. After this, I'll come to this value, and you can see that these two values are equal, right? But this value is 0, so I'll simply write 1 here. And what about this? B is not equal to a, so maximum of these two values is 2. Now a is equal to a, right? Whenever a we have equal characters, so I'll write 1 plus this value, which is going to give me 3. And after this, c is not equal to a, but the maximum of these two values is 3, right? So I have 3 as my output. And what is 3? From this string, if I choose this particular subsequence, which is ABA, so I'm able to get the longest palindromic subsequence of length 3, right? So this is how we can solve the problem using the tabulation approach. Now, without any further delay, let me directly show you the tabulation code, right? So this is the tabulation code. You can see that this particular code is something independent of any recursive call, right? And this is going to save the extra stack space that we were using. So this is the Java code, and this is about the Python code. Now I hope you have understood the problem, every possible solution, and how we move from the brute force approach to the most optimal approach, right? Well, this is all about this video. Thank you.